convert how to convert lead into gold. But nowadays, how do you get rich? Well, you make a cloud hosting company. You don't need any gold because it doesn't matter. This is much better. So like I was thinking, what if I wanted to make my own cloud hosting company? Well, so I started thinking about some kind of system that would be unique and probably as efficient as possible so that I would have as little hardware requirements for as much hosting as possible. And one of the things that I was thinking about was like strings. Everybody needs strings for all kinds of string identifiers, and basically there is no system that doesn't have a lot of strings that name all kinds of stuff absolutely everywhere. So I was thinking, so like this got me to the idea, like, how to actually efficiently handle strings that in general aren't very long, but they need to be still strings. It's not like I just hash them and use those hashes, but then I cannot just get the actual string back of it, or even, well, still risk the problem of collisions. So that's basically how I got myself to this topic. So this reminded me first a bit of history. So, well, legends say that a very long time ago, it was not possible to name functions and variables with names that would be longer than 8 bytes. So, well, this meant that, for example, if we wanted to make a function that was looking for the last occurrence of a character in a string, we had to shorten this out. And, for example, we could make up a pretty intuitive shortcut, s.r.o, which would be generally pretty fine. But the problem is that people living outside of this country generally have problems pronouncing things like s.r.o and so on. So people started looking for other solutions to this problem. But let's not think about these other solutions because you all know them. But think of it from a different point of view. We have a 64-bit architecture. A word is 8 bytes long. And basically this string that is limited to 8 bytes is just one word. And it's a primitive type, and we can just move it around with one instruction, no overhead whatsoever. Or absolutely minimal overhead compared to like strings in many languages when you can generally use a pointer to some garbage collected structure. This is kind of this has the same efficiency, but without the actual overhead of anything else. So, like, yeah, this would be actually super efficient. But on the other hand, yeah, super efficient, but it's just 8 bytes. And people, well, people who don't live in this country generally won't be able to pronounce these shortcuts that would be the result of these short names. So what else can we do? Well, many years has passed since the time, and 8-byte words are no longer the only thing. So now we also have SIMD, which means that we can pretty much just have 16 bytes or even 32 bytes. And more recently with AVX 512, we can get even 64-byte strings, right? Basically, we still have instructions to process variables of this length with just one operation, right? So yeah, I guess we could use this. And one nice thing that also happened is that C++26 is going to have, well, is probably going to have SIMD, which means that there will be a standardized approach of handling this kind of things. Currently, it is only available under the stat experimental prefix. However, it's based on Parallelism TS version 2, and it has implementations in both GCC and Clang, so we are in luck. except for those who use Microsoft Visual Studio. There it's not present, but they will probably hurry really fast to get it done once it actually gets officially released, because they want to be C++26 compliant as soon as possible. So, like, yeah, this is probably the near future. But for now, if you are just using GCC and Clang, basically, we don't even need dependencies to get access to SIMD, which is pretty nice. Oops. I was looking at its design and so on for a while. It looked pretty good, but it was visible that it's definitely not going to get standardized in exactly the version as it looks now. Especially when we were handling actual truth values, so the result of some operations that where the result was either true or false. These were represented as bit fields, and these bit fields, well, were basically just aliases over integer types. But if these were integer types, we could use the bit header from C++20. But it was some kind of wrapper around it that had some features that were quite thought well after, but on the other hand, it had a pretty significant problem, and is that bit is better than that. It was made for good interaction with the SIMD, but actually, when it came to actual operations just with these bit fields, it was inferior. So with NISWA, and I was looking that Intel was actually pointing this out in some discussion, and since this was Intel, who has a big word in the C++ communities, so, well, this probably will be amended and actually will be made more consistent with newer features of C++. But for now, I don't know how it is exactly going to be fixed. But with the stuff that is present here now, we can still do a lot of stuff. Okay, so the architecture, the main class for SIMD is the experimental SIMD. By default, we will template it to some type that is supposed to be inside, like float. In that case, it's some kind of container that holds a certain number of elements that the compiler considers optimal for the platform we are on. We can use a second argument to do some ABI specification to make sure that we won't have problems that the library was compiled for one size and we are having code that was compiled assuming a different size. And it has also some helper functions which will allow us to deduce the size, which is necessary if we want to process a larger chunk of data. But we want to know how large our actual small SIMD chunks are. So, so this way we can actually do it step by step by patches of several elements and using this just one instruction to compute them all. It supports a wide variety of per element arithmetic operations, which is something we don't really care about when it comes to strings, but that was the original purpose of this, doing some computer graphics, making some scene tree where we have vectors of 4 floats, which are used to actually compute the positions of the object in space, and we can use it very fast. But, well, since then, its usage has greatly expanded. Yeah, another part that is pretty much essential there, though it's not so absolutely necessary for computer graphics, it's stud experimental SIMD mask. Basically, it's just a bit field, and it holds the result of some comparisons or other operations with a binary result. Well, no, I mean Boolean type of result from individual elements. It supports a few nice operations to like put all these values together, like all of, any of, find first, set, and so on. But well, these are quite nice, but well, as I said, the bit header from C++20 is better, which makes it kind of tempting to sometimes just reinterpret CASI to an int and then use int and the bit header on it. In case we need a certain specific size that we don't want to use the one that's optimal for the platform, we want to force a certain size, we can use the experimental fixed size SIMD and use the first argument is the type, second argument is the number of elements. This will force the size. If it's not optimal for the platform, doesn't matter. If the platform doesn't support it because we don't have like 17-byte SIMD, well, bad luck, you'll get a compilation error. Yes, another thing that was part of the title is branchless programming. We will delve into this a little bit, but it's not like an absolutely necessary part. But I will make a short introduction into this topic. Branchless programming is quite unexpectedly some code when we don't have any branching. Well, the advantage is that the probability of branch misprediction is 0%. I mean, the probability of branch misprediction in a certain section of code, because if we're trying to like the probability of branch misprediction in a specific condition, then well, we would get undefined because we are dividing 0 by 0. There are no ifs, so we cannot. So like we cannot count it. Of course, there are obvious disadvantages of this. Like first, we may spend so much time confusing things we don't really need that in the end we should just do an if and not compute these things that we don't need to compute. The code often looks worse because it's a little confusing that we were using some mathematical tricks to avoid an if. And just to get this working, we need to think about some mathematical tricks, how to even just avoid making the conditional operation and end up using some special instructions for this, like conditional move. There are other things. We can just do some arithmetic that results in the the Boolean that we want, but never completely straightforward. Quite an easy way to prevent the compiler from emitting an if is to use the multiply by bool. So in the branch, so if we do branching, we just, this is obvious, yeah. If we want to avoid the branching, we can multiply by the Boolean value. Ternary operator sometimes works. The pitfalls that requires us to actually check out what in Godbolt what it does is that is that because there may be some problems. Typically, if we multiply by bool, this may result in integer multiplication, which may or may not be better than branching. But generally, we don't need to become something like conditional move, which is definitely cheaper. And another thing that usually, and for a ternary operator, the problem is that this sometimes may be converted into branching. I am not entirely sure if the compiler actually concludes that it is cheaper to do the branching, or if it just depends on something else. So now let's go to the to the implementation. 108-bit SIMD was added by the start of the millennium. The idea was just to do some 3D graphics with that. These instructions eventually became the SSE instructions on x86 architectures. On ARM architectures, there are the neon instructions. However, in practice, you only had 108-bit SIMD. Larger ones are, well, virtually unheard of. So, but like theoretically, should support up to 2048-bit SIMD. Well, these instructions, but they just won't work. You can get only 128. So a 16-byte SIMD string should be not a big deal, available everywhere, easy to get done. We just need proper C++. So for first, let's declare classes contents. So yeah, let's use the size as a constant. Then we can make this declare a fixed size as SIMD for character and this size. A constructor is not completely trivial because first thing is that is the problem that we are trying to read 16 bytes. When we are trying to form an SIMD structure, it doesn't care how many bytes is in the source, it always copies 16 bytes. So this is this operation, copy from, you just get some data, and I can specify whether it is vector aligned or not, so whether it is aligned as the SIMD structure should be or not. But it doesn't take the size anywhere, it just copies 16 bytes, copies its size. For this purpose, I had to create an array into which I copy the data. The problem is that a string view may be pretty much just completely at the end of an allocated structure, and I might just get out of an allocated area if I continued 16 bytes, which isn't something I want. In that case, I basically need to take the size, the actual size, copy it into a structure, and read from that one. And just to make it a little faster, I made sure that it will be aligned as an SIMD array. And in that case, I can use the vector alignment, which copies it a little faster. Yeah, one obvious thing is that here I have a condition. So it's supposed to be branchless, but I did this for the purpose of basically validating the data. This constructor is would depend on what is our source. If it is just some buffer we are parsing from, we can just ensure that there is a little more data at the end, so we can just copy the data from it and not care. But well, we might also possibly just cut it out and just assume that if it is larger than 16 bytes, it doesn't matter. So there are many options. So like this may be branchless as well. That would be trivial, but in here, I thought that this validation would be probably more practical. Yeah, there are some remarks. I forgot anything? I don't think so. Yep. One thing I noticed is that the structure is trivially copyable, and the data member, which is like the only member variable, is internally represented as a 128-bit integer, which means that it is copied as a single instruction. Which looks like, at least at this point, we wouldn't even need SIMD if in C++ we could do UINT 128T, but yep, we don't got that one, which is a little sad, but yeah, internally it is exactly what it could be. And we are copying it with a single instruction. I was looking at Godbolt, but if this is just some mov with keyword as an argument. Yeah, here is the implementation. So if you want to experiment with it, yeah, I will show it later when we'll get into something more interesting. Yeah, so let's just go through the operations that we might want to do with it and show how this actually looks with SIMD. First thing is size. As you know, I'm not keeping the size as a separate variable in the string, which means that we need to be able to compute it super fast. If you remember how the constructor was written, it was written in a way that all the unused bytes in the string will be zeros, which means that if the size is 16, all of them will be used. So how to do that? We can compare each of these elements with 0, like element-wise comparison. And this way we get a bit field whose individual bits tell whether the byte in the SIMD object was zero or non-zero. And then we just find the first one that was set. Which, well, means that this is basically this. Well, this is not a single instruction because it requires actually having an array of zeros that is SIMD and compare this to SIMDs element-wise in order to get the result. And there is just one instruction for getting the first one, that is 1. We can have a look at it in Godbolt. Where do I have it? Yeah, here.
I mean on Zoom, not.
Wait, on Zoom? I thought I was sharing the whole screen on Zoom.
I'm sharing on this.
Okay, so I just share screen and desktop one. Yeah, but now I have this stupid thing over here. Okay, so now I switch to this thing and okay. So size is the first operation. It's pretty short. It's like I don't know why it wasn't even completely inlined, but I don't have a touch screen.
I know you don't. I'm just pointing.
Aha. Okay.
Okay, maybe not that much. That's good actually.
Okay, so yeah, I don't know what is this XOR even doing here, but the important first thing is that yeah, this is an SIMD comparison. This one is creates a mask made of the most significant bit, and then this TCNT counts the number of trailing least significant 0 bits. So this is pretty short. It's not just one instruction, as you see, but well, 2 instructions, but we are fairly close to that. Yeah, there is a little problem with the standard with the parallelism we do TS, and it is that find first set is undefined behavior if there is no 1 bit anywhere. If all bits are 0, it is undefined behavior. Because like it's supposed to find the first one that is set, and if none of them is set, then what is the result? Well, they kind of decided this is undefined behavior. I don't know why. If I look at a very similar function in the bit header, it basically is defined differently and count leading zeros, which tells exactly which emits the same instruction as this find first set, with the difference that count leading zeros clearly tells us that there will be that we don't need any 1 bit anywhere, but there may be just zeros all the time. And if we have a 16-byte string, then there is, and all of them are zeros, then we get 16 because there are 16 leading zeros, because all of them are zeros. And in that case, it's actually defined, and it emits absolutely the same instruction as this find first set. So it's declared to be UB, but actually tells you the size of the size of the bit set. So which is like, I decided that I will not be casting it into an integer and then calling the count leading zeros. I will just use it the way how they meant it and expect that when it becomes mainstream, they will actually fix this issue and define it as like count leading zeros instead of undefined behavior if all of them are zeros. Okay, that's all for size. Let's go to comparisons. Want to check if two strings are the same. Now we just do a comparison between the first SIMD structure and the second SIMD structure. In that case, we get again a bit mask, whether they are equal or not. And we want all of them to be the same. So we just use the all off and we check if all of the bytes are the same. All of the bits are the same, which means that if like that means that we expect this to be 0xFFFF, because well, we are just comparing strings, comparing integers in this case. So I'm not sure if this was it wasn't inlined. So yeah, we are comparing it with -1, which is probably unsigned, so we get 0xFFFF. Yeah, this is just some other stuff. Here we have one move, and here are again the same two. Yeah, the same two SIMD operations like before. So again, we can do a comparison this fast. Well, yeah, there is nothing new. Yeah, the spaceship operator. Why was I was defining the equals operator first because, well, it's simpler because it's a good thing to start. But more importantly, if we use if we define the equality operator, then and also the spaceship operator, then the equality operator will be used if we are actually comparing, like for equality, which is equals or not equals, so that it will synthesize the not equals operation. But the actual comparison, like which one is greater than the other, will be synthesized from the spaceship operator. And because we can compare it faster than, well, do the equals comparison faster than the spaceship operator, then, well, we want to specify it anyway, just for the purpose of making it faster. This code is not so simple anymore. First, we check which bits are greater in the first string. Next, we check which bits are lesser in the first string. And we want the first bit that is greater to be actually like have a earlier position than the one that is lesser. Which means that again, in the end, we want to do the comparison. And then we find the first that is set in both. And now we want to do a little bit of arithmetic to avoid some unnecessary branching just to get the result. So we can compare this. We get a bool that we save as an integer, which means that it's 1 in case the first greater is really greater and 0 in case the condition is false. We actually want to want from the spaceship operator to give us a positive number in case the first one is greater, negative number if the second one is greater, and 0 in case they're the same. After some thinking about this, I realized that probably the shortest way of doing this is to multiply the previous value by 2. And in that case, we get 2 in case it is greater and 0 in case it is lesser. And then subtract the comparison if they are different. which means that if they are the same, the 0 will remain 0. If the first one is greater, the 1 will be turned in, the 2 will be turned into 1. And in case the second one is greater, the 0 will be turned into -1. So we get the range we wanted. So when I look at the assembly, it's far more complex. But it looks like the same operations as before, just they are all duplicated. And then here is the math we were doing to compare them. Well, to get the range we need. I am not sure if, because it doesn't seem to be inlined, this means that actually this math will be done and it will not be able to do much optimization at the place where it is used, which is unfortunate. Yeah, there is some description. Yeah, here is an important note that some old processors don't have one of the instructions that is needed there, the TZ-CNT, which counts the leading zeros, I think, something like that. So we need to add a compiler flag MBMI. But in practice, I was trying it on a laptop that was like 5 years old and everything was fine. I assume it will work pretty much anywhere now. Next, so finding something. Finding a byte in a string is basically similar to finding size. We just don't look for 0, we look for something else. However, the only thing that makes it more complicated is that we need to return as that string npos in case it wasn't found. But so basically we need to check whether it was actually found and where was it found, and then use the ternary operator. The ternary operator does, well, I have experimentally found that this one results in conditional move, which is the fastest in this. Oh, well, the fastest way to do something branchless. If I look into Godbolt, then find is, well, not very long, but we have a few extra instructions for handling this replacement with a constant in case it's not found. And now to add something more complicated, let's do the to-lower operation, which is useful if we want to make case insensitive comparisons. If we were doing it for to support also non-ASCII symbols, this would be far more complicated. So let's just stick to ASCII. So the to-lower function, I wanted to create a copy of the string that would have all of the uppercase characters converted to lowercase. So first thing, we need to copy it. We don't have a copy construct, or maybe we have, I'm not sure why I wrote it like this. But anyway, the interesting part is that we need a bit field that will tell us which bytes in the string are uppercase. So the condition is that first we find out which ones are greater or equal to uppercase A, which ones are lesser or equal to uppercase Z. We get the logic, like the logic end of this, which is written like if this was an if condition, which is a nice use of operator overloading. But in practice, we just do an SIMD operation here, SIMD operation here, and then bit end here. So it kind of makes it look like makes it look like a normal condition, but actually it does the SIMD operations, which in my case I like this design. Next thing is that we need to conditionally assign to the lowercase value to some elements, which for this, we have this where function. It takes two arguments. One is the thing that we are trying to modify. The other thing are the condition that telling which ones to modify. And we get some kind of object that has overloads. And into this overload, we can assign, or we can make some make some assignment modification operations like plus equals. And in that case, we just get the difference between uppercase A and lowercase a. I don't know how much it is, but if we add this value to every uppercase character, we get a lowercase character. So we just in this place, we create a copy of the original assigned structure. We make this addition to every element, but we conditionally assign only those where were uppercase previously, which makes the whole thing lowercase. To look at the assembly, it's fairly long. I am not sure why all these operations are needed, like p-shuffle, which shuffles the bytes in the SIMD array. I am not going to explain all of this because I don't really know what all of these mean, but I was testing it, it works as expected. Okay, the description isn't important. Yeah, one problem is that the where operation will actually emit some conditional code, because this instruction to conditionally assign something to to elements in an SIMD structure is enabled by MSSE 4.1 flag, which means that basically it's like the latest revision of the SSE, I think, and it might not be supported on all of processors that are used by now. So we need to enable it explicitly. Well, the last thing to look at is hash. Hashing a fixed size structure with no gaps or any irrelevant bytes that we just do every byte matters. That's a trivial problem. So we can just do a reduce. This is the reduce operation. So we just call reduce, which element, and some kind of functor some kind of that definition of an operation. Stud plus is, I think, a functor which adds two elements. And yeah, the other argument is obvious. So I think there is a template specialization for the stud plus, which means that all of the elements will be added in a single operation. But in practice, well, we are adding a large number of 8-bit values, which means that the result will be somewhere between 0 to 255, which is not a very good hash because we have very little range. Even if the distribution of different strings will be different, we will just get so little range that this will be a pretty bad hash. But like this, I just kept it here for a demonstration what we can do with SIMD, just to also make process all these elements together. We can actually you can use a lambda here instead of the stud plus to do any operation to reduce them together, but I don't think that it will be able. Well, I don't think that it will actually convert into SIMD properly. Now, like we might just tell that, okay, we are satisfied with the hash if we just turned it into 64-bit chunks and edit these together. But, well, the problem is that if you cast one type to an unrelated type that isn't just 1 byte size, it's undefined behavior. which we want to avoid. So the usual approach is to do memcopy, because memcopy kinda is allowed to do this. But the problem is that if I used memcopy, it actually emitted a very large number of instructions. So I had to do it the dirtiest way possible. Oh, this was the nice approach with memcopy, that I just create another SMD which is smaller, and I memcopy it into that, and then I just plus these values. In this case, those are two values, so I can just do plus, or just. But I wanted to scale to different sizes automatically. So this worked, but the problem was that now there was quite a lot of instructions. So I had to do some crazy, my element, sorry for this wrong indentation. Yeah, if I do a lot of reinterpret cast, it was faster. Well, I mean, there weren't all these extra instructions, and it just created the first SMD structure and used the 64-bit operation on it, which is what I wanted, but unfortunately, I had to write it this way. Yeah, it allows some kind of casting, that I might want to cast some integer to float or something, but not to elements of different sizes. Unfortunately, I would love if there was a better way. Of course, these hashing functions would be fast, but of course, it wouldn't be a great hashing functions, because the main problem of this hashing function is still that that we might just swap two parts of the string, and if we are just adding everything together, it would just produce the same results. To avoid this problem, we might multiply it element-wise with some constants, well, some SMD array of constants, which would prevent these positional swaps. But, well, it depends how good our hashing function has to be. So regarding performance, I have created these benchmarking functions that does quite a few operations from those that I had written there. In this case, string is a template argument, and I was using different types of strings that I wanted to compare it with. Random string view results in a string view of a size up to 16, or if I want to try, up to 15, because well, I wanted that string to keep the short string optimization. So I was trying to do this to benchmark them. Originally, I wanted to make the array larger, but for whatever reasons, GCC reacted to this by eating like 5 gigabytes of RAM and taking up to 10 minutes to compile this. At that point, I gave up. I'm not going to solve the halting problem of GCC compiling this. So you are probably curious about the results. When I compare it with the naive implementation of a 16-byte string, where just everything were for loops and obviously some ifs inside and so on, turns out that the SMD implementation was twice as fast, which was quite underwhelming, but I found the answer to this. The point was that first thing, it inlined everything because it knew the size. It still could benefit from it, and unrolled these loops. So, and as a result, it just was able to use so many optimizations on this that, despite the number of instructions, it was surprisingly fast. If I use the string manipulation functions from C, like strchr or strlen, I got only a slightly better performance than the naive implementation, so it was still around twice as slow. But what I have noticed that not all of the C functions were inlined. Overall, the SIMD string and the C function implementation had similar number of uninlined function calls, which seems that probably the C functions do use SIMD, but there's probably some additional overhead of like checking if they can use it or something, or handling some alignments that are not guaranteed anywhere. I was comparing it also to string, which was 3 times slower than the SIMD implementation. I have found in the Godbolt that none of its method calls were inlined. And surprisingly, even the constructor took actually more time than even the constructors took more time than the SIMD implementation. I knew before that string constructor is very slow. I was still surprised by this. For actually this, when I was earlier doing some profiling and I realized that another map using string for the keys was several times faster if I put string view there and build a vector of strings to which that actually held the references to these string views, which was surprising, but actually just the constructor of string are so slow that it's worth it. Yeah, so overall inlining was a frequent problem there. A lot of things, the performance was often just dictated by the inlining speed. I was surprised like how short were these SIMD functions, and they still were not inlined. I don't know what, maybe the compiler is afraid to inline functions that use SIMD. I don't know what was the exact problem, but it seemed like it was behaving that way. Which means that basically if you want to use SIMD as some kind of two abstractions and abstract over it, it might not be zero cost. Which means that if we wanted to do some other string manipulation with SIMD, we might have to actually explicitly use SIMD all over the place. Because, well, if we use some abstraction, it might not be inlined and we would end up with extra function calls. Yeah, I was trying in the GCC and Clang. In both cases, the results were similar. The time spent in the actual benchmark was neglectful. So if something seemed to be 2 or 3 times as slow, it's probably, the number is probably correct. It's like the difference is greater, but just the time spent in the benchmark is constant. So I was trying to use it on larger SIMD structures. This was pretty trivial, just change the constant over there at the start that was defined inside the class. And now there were 32-byte SIMD arrays. The performance was unchanged, which means that whether we are dealing with 16-byte strings or 64 or 32-byte strings, there is no apparent difference. It just cost us more memory usage, but otherwise performance-wise, there's nothing. Looking at the assembler, there are actually more move instructions when copying it because we cannot use move on something larger than 16 bytes, but I didn't notice any difference in performance overall. So it's probably not a problem. Maybe just the processor just abstracts over it somehow. I saw that the 32, with these sizes, the C-style string functions were affected the least, almost not at all. I assume that it's because they are using SIMD as well. Stud string and the iteratively implemented string were the worst now. And the problem is, well, in case of stat string was that now it was dynamically allocated. When we were using the naive implementation, now it actually manifested that there were more iterations. So with 32 character size fixed size strings, we were, well, SIMD was like the benefit was much more significant than with 16 bytes. I was able to run this on a laptop, that was 5 years old, so it's something that's easily available. Unless you are using a Mac with this M1 processor, in that case you won't get anything because, well, they support only 16-byte SIMD. So I tried it for 64-byte SIMD arrays. I needed actually to have a CPU that supports AVX 512. But to enable this, I needed two things. First, get a CPU that supported it. I fortunately do have a AMD Ryzen 7, which supports all of this. Next thing that I needed to do was to specify that I needed to, for this native architecture, which means that I'm going to be March native, or I specify some architecture that supports it, like Tiger Lake. I could compile it for Tiger Lake even on some older laptop, but the result was that it got illegal instruction. The CPU just crashes if it sees, throws an exception and causes a program crash in case it finds an AVX 512 instruction. But what was the problem? That if I just set the architecture to native or Tiger Lake, the performance became worse, even if I actually didn't increase the size to 64 bytes. And strangely, I was on this AMD, but if I specified Intel architectures like Tiger Lake, it was faster than if I specified the native one, which was more confusing than I expected. The difference got actually worse if I used later GCC than an earlier one. And the result was that the data was just so noisy that I couldn't draw any conclusions. Well, I tried. So the thing that was that I actually did observe was that the 64-byte string was faster than the double of 32-byte strings. So we can get some performance benefit from this kind of SIMD as well. But it clearly was not like equally fast than just 32 bytes. It was slow. So it was slower than two 32-byte operations, but faster than it was faster than two 32-byte operations, but clearly slower than a single 32-byte operation, which took about the same time than a 16-byte. Which means that, well, I was doing this experiment in 2023, and that's probably still true. Nothing new released in 2024 yet. So apparently, using AVX 512 is not a good idea right at this moment. Actually, I tried to use Valgrind and it crashed. I found that it was that it had some experimental support for this, but it was very fresh. So I think I'd say the world is not ready for AVX 512 yet. So we're talking about so far only about string manipulation, or just using strings as some identifiers. So what else could we do with this? Well, we still can do string search and parsing much faster using SIMD. So things like human readable data, we can find the delimiters faster and some escaping and so on. For example, HTTP headers are much faster using the, the parsing of HTTP headers could be made much faster with this. There is a JSON library that is super fast that uses SIMD. It does it does, well, it uses SMD to parse absolutely everything inside this JSON, and they managed to get it into performances that were pretty close to 1 byte per instruction. Well, slightly slower, but they were pretty close. It's called SMD JSON. There was a YouTube talk about it, but they didn't go much into the details of these SMD of these implementations and how they can use it in their algorithms. But yeah, it is there. It's like 3 times faster than the usual fast JSON libraries. So like, yeah, this is a real project and this works. In practice, like other structures, there are 16-byte structures that just are naturally 16 bytes. And if we could just use it as one primitive type, we could get some advantages. Things I could think about are IPv6 addresses and GUIDs. But on the other hand, they would benefit from being represented as 128-bit integers, but on the other hand, we don't need to do many operations with them, which is like, yeah, the advantage isn't so large. And I didn't come up with other examples. So let's come to a conclusion. 128 and 256-bit SIMD instructions allow implementing very fast string manipulation, which means that we can have very efficient strings of fixed sizes of 32 or 16 bytes. They are readily available through the experimental SMD library, which is quite well designed, but there are some flaws that still need to be corrected. Otherwise, we need some nasty workarounds. And also the compiler, like another display that this is not completely perfected yet, is that the compiler, well, didn't seem to be very fine with inlining the SMD instructions. Well, inlining functions that contain SMD instructions. It looks like the support for 512-bit SMD instructions is not great. It does improve performance sometimes, but like there are many additional problems just by having them somewhere in the program. But I believe that in the future, they might become more widespread and like better supported. I suppose like the compiler, the processor vendors will care about this, because now it's like the only, well, now it is a clear advantage that AMD 64 has over ARM designs, which makes it still competitive. So I suppose they will care about this. And in the future, if this gets properly supported with no performance hits, it will allow us to improve some processing quite significantly. And older CPUs that have like this half-assed support for AVX 512, like the ones that we have now, will still be usable because the programs get compiled to use AVX 512, and yeah, we can still run these programs. They don't run super fast, but at least they still run and we can use them. So I think it's still useful for them to be there, but probably it's better not to compile programs to use AVX 512. That was all. Do you have some questions?
Maybe if I can ask.
Yeah.
Did making the methods const expr make any difference with regards to mining? Or
I didn't think about it at all.
Okay.
Since I have it in Godbolt, I can just try it right now. So, for example, what?
Try size it small.
Yeah, okay. Compilation failed. Yep, this is an annoyance that I noticed. None of these functions are const expr. just it hasn't. I think that the parallelism TS was from before the const expr was. Well, it was from before C++20. I'm quite sure from that, and as a result, there are some problems with it that many functions are not const expr. I wanted to make well, especially constructor is not const expr, which was a little annoying that I just cannot make compile time constants that would result in some SIMDs present somewhere. So yeah, this was actually also criticized by Intel, if I remember the paper that they published. Yeah.
We have seen that actually the experimental sim there has iterator recall, so we don't need to define our own iterator recall. You could just default it.
It has an equal operator, but it will give you a bit field, not a Boolean value.
Okay.
It will give you a bit field of individual elements compared together. So you compare it element-wise. You don't compare it like 128-bit integer with 128-bit integer.
Yeah, thank you. And does it have space operator?
I don't think so, because spaceship operator was from C++20 and the TS was earlier than that.
Okay. And one more question.
Mm-hmm.
Why do we always pass argument by constraints if you believe that it should be only one register?
I don't know. Why was I doing this actually? It's not, yeah, because I was trying it for 32-bit and 64-bit. Wow, 32-byte and 64-byte strings. And in that case, it's like you actually have to copy it. Only the 16-byte ones were single instruction copies.
But maybe for our string 16, it will improve
yes, for the string 16, it would be well, it would definitely removing this const reference wouldn't harm anything, but with the 32 and 64-byte ones, it might harm performance. But I might just try it out what happens if I take this operation and remove the const. What happens? I don't think it will make any change. Oh. I don't see any difference, and the invocation itself. Where is the usage when I was trying? So here was the comparison. So where was this comparison? Maybe I can, yeah. Yeah, it is actually, no, here is actually a function call still. So nothing, no benefit, looks like. So yeah, it doesn't make it doesn't seem to make a difference for 16-byte ones. Oh shit. What was, I think I'm dehydrated. Never mind. Yeah, I think it doesn't make a difference for 16-byte ones, and for larger ones, well, you do avoid some copying. So, like, there is a minor reason for doing that, but I don't think it is of any particular importance.
How much faster do you think it would be if you use just the normal Intel API or Sim?
Intel ABI?
API.
You mean those just...
Those underscore something.
Yeah, that one. I don't know. I wasn't trying to use them because, well, I don't like think they're compiler specific because they tend to be type agnostic.
Won't there be that the compiler doesn't do any optimization on those?
I don't think that's true, but I think the problem was that it generally tends to ignore types. So it makes it generally more error prone, and I don't like using compiler specific things. But I think, well, I didn't really try it, but when I was trying different optimization levels, at least like 01, there it already got to this point that it was able to inline basically everything that was called from well, basically all of the methods. There were no calls to the actual template methods of the experimental SIMD, but like no optimization level actually inline these functions. Well, my functions. I don't know what's the cause. Maybe what you are telling is true, but at least that didn't seem to me like it could be the culprit. Yep.
What happens if you have an ASCII 0 in the middle of the string?
ASCII 0, you mean 0 byte?
Yeah, so yeah.
Well,
looking at the size function, maybe I don't know.
Yeah, it tells you the position of the first 0, and yeah, in that case it breaks because it will behave incorrectly, because I was assuming that the string view it is constructed from will not contain an actual 0 byte anywhere.
Okay.
Because, well, if you look at it, it uses now termination, and like if you try to insert 0 into it, well, the logic stops working. Just if you used the string and inserted 0 in the middle, it would behave inconsistently. You get a C string from it, then you do some strlen on it, you get a different result than if you just got the size of the string. So yeah, this is not something that would work. I think that generally the constructor should take care of it, and I was assuming that I would be parsing something from some source and I wouldn't just get this situation. It's just I had a use case in mind, so this wasn't possible. It wasn't possible in the use case I had in mind, but it could happen with the interface it had.
So just out of curiosity, what was the specific use case you were thinking of?
Well, I was assuming that I will be parsing some input somewhere, and it would be, I don't know, some text file, whatever, something human readable, and I would just find a string somewhere finished by a delimiter, and I would just grab this section from there. So that was what I had in mind, and just it wouldn't happen there that you have a 0 in the middle of a file that's supposed to be human readable. If you have a 0 there, it's a binary file, and then things are different. Yep.
Perhaps only a related question. In the hash implementation, you said that you used root turbid cast instead of memcopy, which I think you showed previously, and then
yeah, I showed the memcopy, and then I used the well, here it is probably too small. Can you see it? Or
yeah.
Okay.
The question is, I thought that it should be equivalent, and the compiler should optimize out.
Yeah, I was expecting that too, but it wasn't happening.
Yeah. Any idea why?
I think that the problem was that it was generally kind of unable to do some optimizations. It was already having problems with inlining. Maybe this was also the thing. There are probably as far as I know, the compiler has some sets of code transformations that it uses to optimize the code, and I think that many of them were assuming that the SIMD instruction wouldn't be there. They were just assuming that there would be normal types. So I think this was the thing that was preventing some optimizations. But I assume that this will get better once that SIMD is part of the standard and it will appear in the benchmarks and so on.
We could also try stability cast instead of Meetup.
Yeah, but I wasn't thinking about that. Any other questions? I can search through the slides if somebody to remind you of things you may have forgotten, or if we can add. It's up to you. No comments. Okay, so let's end now.